So the first system shown below is somewhat similar to things that have been talked about in class, but the next two show something called a block and tackle, where you have a string or a rope that is threaded between a number of pulleys, and it's usually designed to lift heavy weights, and you'll see that in a second. So let's just quickly review the first situation here. You know, if I have a heavy weight down here of 100 newtons, and this rope is attached to it, if I pull at a constant speed, okay, so for this slide, we're going to focus just on constant speed situations here. But if I pull with a constant speed, then I have to have an equal amount of force pulling up, and that, of course, is the tension in the rope. So the tension in the rope has to be 100 newtons, and that means that I would have to pull with 100 newtons. Now, what's also interesting to note, or will be important to note, is that if the block or the weight moves upward by 10 centimeters, then I would have had to pull the rope 10 centimeters. That may seem kind of obvious right now, but it will change as we get to the next few situations. So in this second situation, we again have our weight of 100 newtons, and so we would have to have 100 newtons pulling upwards in order to move at that constant speed. But because there are two ropes wrapped around a pulley, this side will pull up and so will this side. And these are the same pieces of rope. So the tension is going to be the same in each of these pieces, and it's also going to equal the tension that I would have to pull with to move this at a constant speed. But because of the fact that there are two, like a single rope wrapped around the pulley ends up pulling twice upwards, that downward force of 100 newtons is being lifted by these two equal amounts of force, and so each one is only 50 newtons. So you can see this is what allows us to lift up a heavier object with this block and tackle, is because I only have to exert a force of 50 newtons over here in order to lift 100 newtons of weight. But you don't get something for nothing. If I lift this 10 centimeters, then this rope must also move 10 centimeters here and 10 centimeters here. So that's a total of 20 centimeters that I have to move the rope, and so that's sort of what is lost. This is a lot of times discussed in the idea of mechanical advantage or simple machines, that you can reduce the amount of force needed using this machine, but you double the distance that you have to pull for. Looking at this last situation, you'll see a similar idea here. If I arrange the pulley system so that the rope actually pulls 3 times on that pulley, then the total tension upwards is 3T, balancing the weight of 100 newtons down, and so each tension force is actually only about 33 newtons. And so my pulling force only has to be 33 newtons. But again, the distance is different. There's what some people might call the conservation of the string. I have to pull this rope, and this rope a distance of 10 centimeters. And so that's a total of 30 centimeters over on my pulling end. That distance is going to be related to acceleration in the next problem when we try to solve a system that actually changes speed. All right, so this system does not have an outside or external force pulling on it, an applied force. It just has masses that are allowed to move. So if I were to release this system, depending on the weight of the red block or the blue block, the system might move such that the red block moves down and the blue block moves up. Okay, but in fact, what happens in this situation, what we're told, is that the blue block moves downward, so that's the positive direction for it, and the red block moves upwards. And so I'm going to take that into account as I write some equations for F equals ma. So on the red block, the tension in the rope would be what's pulling up, so T minus the weight, so T minus 30 newtons, equals this mass times the acceleration. Now, I'm going to have to just call this A1. I cannot assume that the acceleration of the blocks are the same. They won't be, because the rope will move twice as far here as it does here. That conservation of the string idea from the previous problem. And so I'm going to call this A1, and then for the blue block, it moves downward, and so the 40 Newton weight would be the positive force minus, okay, now you got to look here, there are two tension forces that are pulling up, not just one. Okay, so I have a tension force here and I have a tension force here. So 40 minus 2t, that is going to equal 4 times a 2. Okay, so I have to define a different acceleration for each one. But because the red block will move further in the same amount of time than the blue block, it will also travel with a bigger acceleration. The acceleration of the first block is going to be twice as big as the acceleration of the second block because the string moves twice as far. That's kind of the way that you can think about it. And so if I was going to solve this equation, the system of equations, I have to first take this expression here, this 2a2, and I need to plug it in here. So I get t minus 30 equals 3 times 2a2, or 6a2. Okay, and then I want to combine these together. It would be nice, though, if I had the same t here. So I'm going to multiply this side of the equation times 2 and this side of the equation times 2. So I get 2t minus 60 equals 12a2. Okay, and then I would be able to solve that equation here, or add, I should say, add the two equations together. I can't get my 2 to look like a 2. So I'm going to add this equation and this equation, and I get 40 minus 2t plus 2t minus 60. And you can see that I have come up with actually an impossible situation here. So I have negative 20 equals 16a2. Okay, and what I get then is that my acceleration would be negative 20 over 16, negative 5 over 4, so negative 1.25. Now, how can that be? All right, well, that tells me that this assumption that the 4 kilogram block moves downwards is actually a false assumption. This system would not move in that way. It would move in the opposite way. Now, do I have to go through and recalculate? No. If there's friction in the system, I might have to do that. But in this case, this just tells me that the acceleration of the blue block is actually getting ahead of myself here, is 1.25 meters per second squared, but instead of it being down, it's actually up. Okay, and then for my red block, because my A2 is twice as big as my A1 is twice as big as my A2, I'm going to double this. And again, I had originally assumed that this block was moving up. It must actually be moving down. So in some cases, you don't know which direction something's going to move. You just make an assumption and then look to see what happens. And in many cases, if it comes out negative, it just means you picked the wrong direction.